So we're talking about our Laplace transforms, and we've been building up a library. So we have a library of functions, things that we know how to take the Laplace transform of, and then we have a couple of rules for things like, oh, if you multiply by the exponential function, the result is to shift the output. If you take a derivative or a second derivative, then essentially you multiply by s and you have some extra terms on the end. So we're going to add to our list of rules today. So, for example, we talked about how to take the derivative. Now we'll talk about how to take the antiderivative. And if you see the rule, you're like, oh, when we took the derivative, you multiplied by s. Antiderivative, you divide by s. Who would have thought? Okay, well, actually it's not so crazy. We'll also do things such as saying, hey, if you take the transform of t times a function, the effect is negative the derivative of the output. So there's this beautiful symmetry. See how we come up here and say, hey, if you take the Laplace transform of the derivative, you multiply by this s. And here you say, oh, if you multiply by t, it becomes a derivative. So there's this wonderful, nice balance that goes back and forth. Of course, once you can take one derivative, you can take many derivatives. That's that rule. We'll apply it to sine and cosine. And then there's this weird thing at the bottom, which we'll talk about, which essentially says, how do you handle multiplication? And we'll get to that. So that's where we're going, adding some rules. We'll start at the top. Okay. So the first thing we want to talk about is how do we take the transform of the antiderivative? Now, I want to point out this isn't just any antiderivative, because we're going to use some facts about this, because we have specific bounds. So this is the antiderivative of f with a particular initial condition, and namely, what can you say about the value at 0? What is g of 0? When you plug in t equals 0, what do you have? 0, right? Because we have the integral from 0 to 0. So essentially, this is the antiderivative, which has the initial value 0 when you plug in t equals 0. And now we say, okay, well, let's find the Laplace transform of our antiderivative with a special initial condition. And there are two approaches here. This isn't like step 1, step 2. Here's approach 1, here's approach 2. The first approach is to say, well, you know, there's a relationship between f and g. We think of g as the antiderivative of f, but we can also say, oh, if you take the derivative of g, that's f. So we say, all right, so if we take the Laplace transform of f, we have a name for that, that's capital F. And since f is equal to g prime, that's the Laplace transform of g prime. And then we say, wait, hold on. We know how to take the Laplace transform of derivatives. So that would be s g of s, because here our function is g, minus g of 0. But we know g of 0 is 0. So that's s times g of s. And therefore, just dividing, that says that g of s is f of s over s. Okay. All right. Now, that's one method. And if you like, that's all you need to know. If you say, well, could you do it another way? Yeah, we're getting to the point where there's lots of ways to solve things. And another way we could do it is integration by parts. So you say, okay, we have the definition for the Laplace transform. So we plug it in. Say, all right, that's integral e to the minus st g of t. And we'll let u be our g of t. Then we do integration by parts. So we have our uv minus the integral v du. And here, the important thing is the derivative of g is f. And now, when we plug in our bounds, well, g of 0 is still 0. And when we go to infinity, e to the minus st goes to 0, so that disappears. This minus 1 over s can come out as a plus 1 over s. And then you have e to the minus st f of t on the inside, which becomes capital F of s. So there's another way to derive that result. All right. Now, how do we use this? Well, let's suppose we want to find the inverse Laplace transform. 1 over s minus 3. Okay, now if we had done this last week, what would we do? Partial fractions. And between me and you, that's probably what I would still do. But just to show you, there's options, right? It's nice to know that we have options. So you can do partial fractions, but this will do it without doing partial fractions. So how does this work? Well, the idea is to say, well, you see this s here. We can really think of this as the Laplace inverse of, and then our function is 1 over s minus 3 over s. So in other words, I'm thinking of here, this part is my capital F of s. All right. So I've written it in this form, f of s over s. Now, what does that tell us? Well, it tells us that this Laplace inverse, if we follow this rule, it's going to be the corresponding g. So that this is going to be equal to our integral 0 to t of f tau d tau. Now the question, of course, what's the right f? Well, do a little bit of work on the side. So we have, if capital F of s is 1 over s minus 3, then in general, f at t, that's the inverse Laplace transform, 1 over s minus 3. And what would that be? e to the 3t. So, picking up, say, this is going to be equal to the integral from 0 to t, e to the 3t, sorry, e to the 3 tau. So tau is just another fancy way of saying a Greek version of t, d tau. So now we integrate. What's the integral of e to the 3 tau? Yeah. 1/3 e to the 3 tau. Evaluate from 0 to t. We end up with 1/3 e to the 3t. Subtract 1/3 e to the 0, but e to the 0 is 1/3. And there we go. All right. Should we check it with partial fractions, or do you just trust it? Trust it. Oh, you just trust it. Look at you. You're so trusting. Well, good. Good. So anyway, so that's the idea. So when you see a 1 over s, you can say, I can think of this as taking the antiderivative of what would happen if I took the inverse Laplace of the rest of it. Now in practice, I really don't think it's that much more efficient. And personally, I would probably stick with doing partial fractions. Because I like to keep things simple. But that's just me. That's just me. All right. So we're ready for our next rule to add to our list. So for our next one, we're going to start with our definition for taking the Laplace transform. And now we're going to think, okay, here's a function of s. There's a function of s. Let's take the derivative of both sides. All right, that doesn't seem so bad. So we start saying, all right, well, f prime of s, that's the derivative of this expression. Now, there's a small detail. It says, well, you have an integral and you have a derivative. And can you push the derivative inside? That's what this little blurb says. Are we okay? And it says we are okay here, but it's not so clear. But all right, so the moral is we're moving this derivative to the inside. So we say, all right, push it in, and we say the only thing that has an s is this exponential part. So it's really the integral of the derivative of e to the minus st. All right, well, that's an easy derivative. Now remember, we're taking the derivative with respect to s. So when we take the derivative of e to the minus st, in this point right here, just covering that up, at that stage, when we're taking that derivative, t is a constant. So when we take that derivative, what's going to come out is minus t e to the minus st, because the constant comes down. All right, so we take that derivative, and then we just gather a few things. The minus comes out in front. The t joins with the f of t, and then we say, aha, that's minus the Laplace transform of t f of t. And so in particular, if you move the minus back over, this is where we get the idea that the Laplace transform of t f of t is equal to minus f prime of s. All right, so that's that derivation. Okay, that's not so bad. Now, you might say, okay, well, what if we repeat? Well, so if you think about it, if I have t to the n, I just repeat this process n times. So what's happening in the process? Well, you're going to get a minus every stage, so that's why you have a minus 1 to the n. And you're going to take a derivative at every stage, which is why we get up to n derivatives. So this idea here is basically just saying, all right, repeat our rule n times. All right. Well, let's use this. So let's find the Laplace transform of t sine of bt. All right. So in particular, we're looking for the Laplace transform t sine of bt. Now, on a side note, if we did this by the definition, it would take a while, because what would be the integral? Well, it would be the integral 0 to infinity of e to the minus st t sine of bt dt, where we'd have an exponential function, a trig function, and a t. Now, if we look at this, we might look at this and say, ugh, which is our way of saying, that does not look fun. So yeah, we don't want to go to the definition. That would take far too long. So what is it we're going to do instead? Well, we're going to use what we just learned. Say, oh, okay, so what's the key? Well, the key here is we need to say, what's happening to that sine of bt? Well, do we have the Laplace transform of sine of bt? Well, yeah, we do. It's b over s squared plus b squared. Yes? All right. So we make a note. The Laplace transform of sine of bt is equal to b over s squared plus b squared. Okay, well, this right here is our f of s. So when we take the Laplace transform of t sine of bt, that's going to be equal to minus f prime of s. And we already know what f of s is. All right, so really, we can say that's minus, we'll write it out really explicitly here, derivative of b over s squared plus b squared. All right. Well, how do we take this derivative? Ooh, a quotient rule. Okay, all right. We can do a quotient rule. There is another thing we could do if you like. If you don't like what I'm about to write down, we'll go to quotient rule. You can rewrite this. The b is a constant, so we don't need to worry about that. And s squared plus b squared to the minus 1 power. Yes? Sure? It's not. I'm not lying to you. I promise. This is what it is. And then we can use a chain rule. Okay, so we have the minus in front. The b is a constant. When we take this derivative, the minus 1 comes down. And it's s squared plus b squared to the minus 1, so that's minus 2. And then, chain rule says we multiply by 2s. Well, two negatives make a positive. So upstairs we have b times 2 times s. So let's see, how did I write this? So that's 2 times b times s. And downstairs, s squared plus b squared squared, which is what the minus 2 power represents. And there we go. Life is good. All right. Well, shall we do the other one, or do you want me to just write down the result? Same process for t cosine bt. Slightly different steps. Do it. Do it. All right, so let's just remind ourselves. The Laplace transform of cosine bt is s over s squared plus b squared. So the Laplace transform of t cosine bt, well, that's going to be minus the derivative with respect to s of s over s squared plus b squared. Now here we do actually have, the reason I didn't jump to quotient rule was because there wasn't really a function upstairs. It's just a number. But here there is actually a function upstairs. So this is a time when quotient rule makes sense. So this would be, there's a minus. Then we have the bottom, s squared plus b squared times the root of the top, minus the top, which is s, times the root of the bottom, which is 2s, all over the bottom term squared. Well, if you work that out, you have a s squared subtract 2s squared, which makes this a minus s squared. But then there's another minus here, so don't forget about that other minus. So when you put those all together, you end up with a positive s squared minus b squared divided by s squared plus b squared squared. And there you go. All right. So these are some ways, if you ever have t times something, like, I know what that is. Well, then you can use it. All right, so that handles a lot of our rules. Any questions? We'll come back to this in a little while and do some fun stuff with it. Okay. Well, the last thing for our list of rules is convolution. Now, this is kind of unusual because when you see it at first, you're sort of like, huh. And then after you look at it for a little while longer, you're like, huh. What is it? Well, the idea is you have two functions, and you're making a new function. So it's this f star g. So this star here, that's going to stand for convolution. And how is it defined? Well, the convolution of the two functions is you do the integral 0 to t, f of tau, g of t minus tau, d tau. And so you're trying to think, well, what's going on here? It's sort of an unusual way to combine two functions together and produce a new single function. So we say, okay, all right. Now, you might say, why this definition? And it kind of jumps out of the process here. Now, there is a note here. It doesn't matter which order you convolute, so f star g is the same as g star f. So how does this work? Well, where this is coming from says, suppose you have two things multiplying, f of s times g of s. So, in other words, I know f of s is the Laplace transform of something. I know g of s is the Laplace transform of something. And I say, all right, there's my expression. Where did it come from? So in other words, which function results in this multiplication? So we start by saying, well, let's write down the definition. The Laplace transform for f is our first integral, where here I'm using x as a stand-in for t. The Laplace transform for g is this second integral, where now I'm using y as a stand-in for t. All right. Well, so far, nothing too crazy. And now we start sort of doing a little bit of Calc 3 manipulation. We put things together. Say, instead of thinking of these as two separate integrals, let's combine it into sort of a big integral. So we'll turn it into a nested integral. Integral from 0 to infinity, integral from 0 to infinity of e to the minus s x plus y, which is what happens when you multiply these two together. Your f of x and your g of y. Now, the way you can think about this integral here, so if you look at that, that's this integral down here. And what you're really doing is you're integrating over what we call the first quadrant. And you're slicing in this manner. So this is how you're computing that integral. So you're integrating along the x direction, tabulating everything, then you integrate along the y direction. So that's that step. And now we do a little bit of fun magic. So this is the important step. See, that's what the dot means. That's like the magic step. What's the magic? Well, the basic idea is to say, I want this to look like the Laplace transform of something. So in the Laplace transform of something, I should have e to the minus s t. So I want to think of this x plus y as somehow representing my t. So that's what will happen. And what we're going to do is we're going to still integrate over our first quadrant. But now, instead of slicing this horizontal way, we actually slice diagonally. So that's what's going on. So any single slice here, so each diagonal corresponds to a t. And now, as we move along the diagonal, that's our tau varying along the diagonal. So that's what's going on. So this integral became that integral. You changed your slicing. So, okay. And now, you see, here, you always have to go forever, whereas when you do your diagonal, you're going from one end down to the other. So that's why it's a finite integral on the inside. And you push this integral from 0 to t inside because, well, this e to the minus st doesn't depend on tau, so you can move it in. And you say, aha, now I have this expression, which is what we call f star g. So in other words, convolution is what comes out when you actually go through this process. All right. Well, we should practice some of this. Should we compute a convolution of things? Yeah. Let's try a problem. Okay. We'll keep the convolution nearby. Find the inverse Laplace of 1 over s plus 2 times s minus 5. Now, if we were doing this from last week, what would we do? Partial fractions. See, look at all these great things. We're learning how to do things in a more complicated way. You're like, partial fractions works great, but now let's do things more complicated. No. There are things that we'll be able to do which are actually better once we have the right tools. So what can we do here? Well, we can think of this as the inverse Laplace of two things multiplying, s plus 2 and 1 over s minus 5. So in other words, we're thinking of this as our f of s and our g of s. All right. So just as a reminder here, the punchline is, if I have f star g and I take the Laplace transform, that gives me f of s g of s. And so what we can say is that the inverse Laplace transform of f of s g of s, just running it backwards, will be f star g. So we have to start thinking about what's true. So let's start with f. So if I'm looking at f, I'm looking at this piece here. What is f of t? Universal Laplace of 1 over s plus 2. What does that become? E to the negative 2t. All right. And what is our g of t? So again, we look here. G of t, inverse Laplace transform, 1 over s minus 5. What is that? E to the 5t. Okay, so we say, aha, that tells us our answer is f star g of t. So this is what we want. Well, where f and g are these pieces. So let's come back here, just to remind ourselves what f star g is. That's the integral 0 to t, so just copying here. F of tau, so that's e to the minus 2 tau. G of t minus tau, so that's e to the 5 t minus tau, d tau. All right, so we know our answer, just from this rule, is whatever this turns out to be. Well, how do we approach this integral? Okay, so when we have exponential functions multiplying together, we can add exponents. So here, this is the same as e to the minus 2 tau plus 5 times t minus tau. Okay, progress. Now what happens? Well, does anything add?
Should you distribute the 5 through?
Okay, we distribute the 5 through. So we have e, we can write it as 5t, and then minus 7 tau. Okay, is that something we can integrate? Okay, if we can integrate it, what's the antiderivative of this? Okay, negative 1/7. Now, why is it negative 1/7 and not 1/5? Yeah, got to keep track of what you're integrating with respect to. So t is a constant here. We're integrating with respect to tau. So we have e to the 5t subtract 7 tau. And then we're going to evaluate from tau equals 0 to tau equals t. When we plug in tau equals t, what do we end up with? Well, we have 5t subtract 7t, which is negative 2t. Yes? So we have minus 1/7 e to the minus 2t. When we plug in tau equals 0, 5t minus 0 is so 5t minus 0? 5t. Okay. And then we're subtracting that, so subtract a negative 1/7, which makes us a plus 1/7 e to the 5t. And we're done. Done. Okay, so that's an example of how we can use it. All right, any questions? Okay, well, it's been a while. I think it's your turn. Find the Laplace transform of the integral 0 to t tau sine 3 tau e to the tau minus t d tau. Now, in case you're wondering, where did this problem come from? This came from a final from last fall. And your answer needs to be written in the form of polynomial over polynomial. So, for reference, we'll put this here, because this is the kind of sheet you'll have, which has hopefully enough information for you to go on. I'll give you a hint. The right way to do this is not to actually find this integral, because that's a hard integral to do. This is back in our ugh mode. And then people are like, oh yeah, okay. Should we go through it? Yeah. What does this look like? It looks like a convolution, doesn't it? Okay, so let's think about convolution. This should be like there's an f of tau, so I need to have some function of tau, and I need to have some function of t minus tau. Well, do I see a good candidate for something that says, oh, this looks like a function of tau? Yeah, so this integral, we could say, hey, we're going to think of it as two things. We'll think of it as this tau sine of 3 tau. So this is our f of tau. Now, we need something that looks like g of t minus tau. Do we have anything that looks like g of t minus tau? E to the tau minus t, but then I hear a skeptical like, no, it's not t minus tau, it's tau minus t. Is there something we can do to make tau minus t look like t minus tau? What? A negative. So this is e to the minus t minus tau. So here's our g of t minus tau. All right, so far so good? So, move this aside for just a second. What we have is that this expression is really the following. This is our t sine 3t that has been convoluted with e to the minus t. That's what's going on here. So this integral that we've been asked to find the Laplace transform of is a convolution. Okay, and then we say, well, wait. When it's a convolution, I just have to figure out what happens to my individual pieces. Do we know what happens to t sine 3t? Is there anything that can help us figure out what happens to t sine of 3t? There's nothing? I think there might be something. Something somewhere that tells us what happens to t sine 3t. Oh yeah, it's right there. It was right in front of us the whole time. Okay, so we just put in b equals 3. So we know that when we do the Laplace transform, that this is going to go to 2 times 3 times s, which is 6s. Downstairs it'll go to s squared plus 9 squared. What about e to the minus t? What will that go to? Well, e to the minus t will go to 1 over s plus 1. So our original expression is a convolution. We recognize the parts. We know how each one of the parts transforms. So, what's our final answer? These two multiplied together. So, in other words, our final answer will be 6s divided by s squared plus 9 squared times s plus 1. And we're done. That's it. That's the whole problem. So if you know the tools, this can be very quick. If you tried to actually compute this integral, it would take a lot of pages. You'd probably get it wrong. So this is just a way of saying, know the tools. Knowing stuff is good. 4 out of 5 dentists recommend knowing your Laplace transforms. So, all right. Well, any questions? Let's do a fun one. This is one of my favorites. This is one of my favorites. Let's find the Laplace transform of sine t over t. Now, you might say, wait, is that even possible? Is it possible to do this? Well, it turns out that sine t over t looks bad at t equals 0 because there's that t downstairs. But what actually happens to sine t over t at t equals 0? It's technically undefined, but it approaches 1. So the sine t over t looks something like this. So here's our function sine t over t. So it's actually relatively tame. All right, now let's not figure this out by trying to actually carry out the integral, because I don't think we can. That's all right, we don't need to. What is this close to that we do know? Well, it's close to t sine t, but there's something even closer than t sine t. Sine t, right? Let's start with sine t. It's like, start at things very similar. Okay, so, true story. The Laplace transform of sine of t, we'll call that something. What should we call this? Let's call this g of s, just for a moment. Well, we say, okay, sine t, that's so simple, it's on our table. 1 over s squared plus 1. All right, true story, true story. All right. Now, there's another way to think of the Laplace transform of sine t, and that is that this is the Laplace transform of t times sine t over t. Why? Yeah, the t's cancel. Okay, so, question. Does this help us to think of it in this way? Probably, because Steve said it. Is there any facts that we can use? Yes? What's our fact? The Laplace transform of t f of t is negative f prime of s. Okay, so this right here, this is our f. So according to this rule, this is negative f prime of what we want. All right. So let's rewrite this. This tells us that our answer, f prime of s, I'll move the negative across, is negative 1 over s squared plus 1. Now, I don't want f prime, I want f. So how do I go from f prime to f? Okay, take an integral. So what is f of s? Integral of 1 over s squared plus 1. It's arctangent. What? Is that right? Plus c. Ah, but what is c? Oh, say, can we figure out c? Okay, I hear people saying 0. Somebody said infinity, that's a bold c. There's this comment here, which we haven't pointed to, but now I'm pointing at it. We need the function to go to 0 as s goes to infinity. So, that says, okay, s going to infinity, we'll have that 0 equals, what happens to arctangent as we go to infinity? Pi over 2. That's right. Because arctangent, if we graph it, has these horizontal asymptotes. And the top horizontal asymptote is at pi over 2. So we get 0 equals minus pi over 2 plus c. So what does that tell us about c? C is pi over 2. So now we see that, lo and behold, plugging c equals pi over 2, the Laplace transform of sine t over t is pi halves minus arctangent of s. There we go. Yes?
I'm kind of confused how you went from the Laplace transform of t times sine t over t, and how you figure that the f prime of s is just equal to the Laplace transforms of just sine t.
Well, what we said is we're after this Laplace transform. So we're calling that capital F of s. So think of this as right here. This is like little f of t. And now we're saying, well, we don't know how to handle that, but if we multiply it by t, we have sine t, which we know how to handle. Multiplying by t, by our rule, makes it minus the derivative of what we want. So it's just connecting things together.
Why are you allowed to just check?
Well, because t's cancel. Well, but I'm not claiming that this is f. I'm claiming this is minus f prime s. So this is a rule. And so this rule is the rule here, which we derived earlier. This is just saying that the t's cancel. And then this is the fact that we know what sine of t does. So it's another rule. So it's the rules, t's cancel rule, that connects us all together. So I haven't cheated you. All right. Here's a fun fact. This is true. But that's not the fun fact. Remember what the Laplace transform looks like? Well, it says that f of s is the integral 0 to infinity of e to the minus st times sine of t over t dt. That's the definition of the Laplace transform. So here's a question. What's the integral from 0 to infinity of sine of t over t? Have you ever thought about that?
0.
Okay, we've had 0 and we've had pi as possible answers. I think if you average them, you'll be close. Yeah, it's pi over 2. What? Well, look right here. Plug in s equals 0. What happens to the exponential function? It becomes 1. So it becomes sine t over t. So this is s equals 0. But what do we know about f of s? It's pi halves minus arctangent of s. So plug in 0. Pi halves minus arctangent of 0. Arctangent of 0 is 0. So you get pi halves. So there you go. Sine t over t equals pi halves.